like starting the course. So what do we like? What is this course about? As I mentioned, so this, I mean, these are some of them are older stuff. You can see the book here, hardness.mit.edu, and so in this class, I mean, that this book actually, Eric Demain and I started this idea of this one. I think we were working on algorithms so that we need to provide some kind of algorithmic tools for lower bound, which is needed. In some sense, it was the Gary Johnson book that we talk in the book. That was Computers and Interactability, the Guide to the MP Completeness. That has started that, but in 1979, and since then, the area has changed a lot. We have many more areas of algorithms and lower bounds there. And lots of them are conditional as we talk about it. So here in this class and in the book, I mean, that was the idea that somehow the book is out of the several times that we taught it, and of course edited a lot to have the book. So this is a practical guide to proving computational problems are formally hard or interactable. And it can be conditional. This is not a complexity course, but we need some materials. So in some sense, it is anti-algorithmic perspective, but it is algorithmic perspective. So in what sense it is anti-algorithmic? Because we will say, okay, there is no algorithm can do better than that. So in some sense, oh, there is no way to do that. At the same time, that is actually the irony there. The way that we prove that you cannot do that, it is very algorithmic. So how can we do that? This is the whole class would be something based. I mean, this is the things that I. By the way, you are seeing the notes, correct?
Yes.
And I think can you read it well? At least the font is fine.
Yes, it's fine.
Okay. Yeah. So I will use. Okay, let me use the pen as well. Actually, the plan is to write these things here as well. Great. So, yes. Good. So I can now write this one. So, okay. So this is the things that we are talking in this one. This is algorithms and reduction. This is the way that this is somehow it becomes an algorithmic class. What is the meaning of that? It means that, I mean, the assumptions are, so there are something that the people have proved it. I mean, like, for example, SAT is hard, or set cover is hard. Some of them we will take it for granted. We don't need to prove everything. And then we say that assuming that these are, and some of the time we cannot prove anything. We just have some assumptions. For example, about exponential time hypothesis, that we will talk about it, or P not equal to MP. We don't know P not, whether really P is equal to MP or P not equal to MP. But we say that if P is not equal to MP, then this happens essentially. We cannot approximate this problem better than this factor, etc. Good. So these are the assumptions that we will talk about it. So for them, you should just know the assumptions for these important problems in the area which are hard. And then the rest is our reductions. These are exactly the part, this is the algorithmic part. What's the meaning of that? It means that in the reduction, we say that assuming that this problem is hard, again, assuming, because lots of them we cannot prove it now, actually, fortunately or unfortunately. I think probably unfortunately. And in some sense, fortunately, because of something for factoring and others, because the hardness of that is used, for example, for all this crypto stuff. And if somebody can have the problem solved, we cannot use or cannot access to our bank accounts, etc. Because in that case, I mean, anyone else can also access it. And then they can get all the money or any other things. So there is no privacy in some sense. So then we say that assuming that these problems are hard, I can show that my problem is hard. How can we show that this is the part that is the algorithmic part? You will say that if there is a procedure, so that is important. So we have this problem A that we are assuming is hard. Then we have this problem, which is your own problem. Good. What do we show here? We are showing that. So I will show that if this problem A is hard, then my problem B is hard as well. Good. And how do you show that? You will say that, how can we show that? You say that you design some algorithm. So we say that if there is an algorithm, so I will call it alg, for problem B, that is doing better than this time, better than this approximation, better than that, then I can get an algorithm for problem A as well, which is better than this hardness assumption. So how can I do that? Generally, that's the thing. So from this algorithm A, this is a type of reduction, and it will be different for different topics, depending on some context. But general idea is that this algorithm, so this algorithm A can somehow call the procedure of algorithm B. So how do we show that this is the algorithmic part? So say that, okay, I have some algorithm for B that is, you want to say that you cannot do for B better than something. Say, okay, let's assume that there is such an algorithm that can do better than this one. Then I create an algorithm. Inside this algorithm, there might be some other things. You may do pre-processing, etc. But I have some call for algorithm B as well. And whenever I do it, and you may call it a few times, you may call it just one time. I mean, it will be different, dependent on the things. But then this algorithm B, using this algorithm B, I can solve the problem A. Does it make sense?
Yes.
So this part is very algorithmic, because what do? You are solving. You are indeed finding an algorithm for A. You can think about like programming. You are having a program for A, given a module, say for example in Python, there's a module or a function for B. And then say, okay, if it is the case that this algorithm A conditioned on the fact that it has this algorithm B has this guarantees, I can get such a guarantee for algorithm A, but this is better than the assumption that exists currently, or some hardness. So communication complexity, for example, we have proved that you cannot do better than this thing. So this assumption that I have it will be violated. It means that there is no algorithm for problem B that has such a running time, such an approximation, such a number of rounds, etc. Any question? This is very important. This is the whole things that we are doing in this class.
Yes. What kind of reductions will be using?
That's exactly the thing that you will see more in this thing. It will be different for different things. So there are some. This reduction, in some sense, this is that type of algorithms, the type of programs that you need to write for algorithm A using a procedure for algorithm B. So there might be some restrictions because you want to say under this context, you cannot do better. So there are some context related restrictions for these procedures that we will discuss essentially in each chapter or each part of this class. So this you will see it more essentially. Good. Now, there are lots of, the people are working on algorithms, that typical type of algorithm on approximation algorithms, like fixed parameter algorithms, streaming algorithms, parallel algorithms, algorithmic game theory, geometric problems, online algorithms, puzzle problems, and all of them actually the one that we are considering. Probably we cannot cover all of them. Lots of them will be covered in the class, but almost all of them are covered in the book. That's the thing that because the book is just more than just one course, from a few courses, and even these courses at different time had the different topics. So it is more things, but that would be great. So when you read it, you have a very good, so that's also another important thing. You have a very good understanding about these different areas of algorithms, because we define these things and then we talk probably even some examples of them, and then we go to the hardness. So you will know actually all these areas of algorithm as well. And these people, I mean, this is the idea. The people will consider this one, and as I mentioned, there are some restrictions. So the general idea is this one, that you try to. So what is this one? The idea would be like this: that people try to improve it, and they improve the algorithm for this particular model, for this particular problem. At some point, they cannot improve it. That's the time that the people maybe try. A few people try. Maybe nobody could improve it. At that time, you will think about that. Maybe I can prove that actually you cannot do anything better than that. At least assuming some assumption. That's the way that we will consider. First, the priority for a problem is that you design some algorithm. But if you cannot find any algorithm at that time, maybe I am wrong, or maybe I'm not, I don't know, smart enough, or maybe I don't have all knowledge for that, or really this problem is hard. Not only that's the whole idea, that maybe I cannot solve it, but this is nothing. It is related to me that I cannot do that. This was actually a good example that it was in the Gary Johnson is like the first book on this one. You can just search this one. So I think it is Gary, maybe E actually, and Johnson. So that is Mike. This is Michael Gary and David Johnson. So they have this nice book, and this is exactly this one that is they are talking about it. They have a very nice caricature, or like a cartoon essentially, that they say that. So this what they are talking about, NP completeness. So the main thing it is about the NP completeness. And what do they say there? They say that, I mean, maybe your boss asks you to do some task. I mean, then maybe tomorrow, I mean, you will try and say, okay, I cannot do it better than this. But that might be not satisfactory for you or the boss, because it's okay, maybe you didn't try enough, or maybe there are some other ways that you didn't consider it. What can you do? And I mean, maybe that's it. But so it's not proof that, I mean, you may work really hard and couldn't improve it, or you may not spend time essentially to do that. It would be hard for your boss to understand that this problem was hard. However, if what do we do in this class and essentially in the NP completeness is that, okay, if you couldn't solve it, okay, that's fine. I can bring, I don't know, 1,000 other people that they also tried and they couldn't solve it. Maybe they didn't essentially try your own problem, but because of this reduction, you will say that if my problem, I can't do it anything better, then these 1,000 other people, also I can improve their algorithm. They couldn't do that, so it means that that's the best that it is possible at this point. Or if somebody can break the wall, then it would be a great result. That's exactly the reason that, I mean, essentially the question of P versus NP, that is probably, I will say that currently the most important problem. This is definitely one of the 7 problems that they had it. I mean, they have 1 million at least for it. Maybe 1 million is not much nowadays. But it is actually, this is probably most important problem in, I want to say even in not only computer science, in lots of other fields, if not all fields. Because this computation is super important for lots of things. And if we can do some of this more efficiently, you can do it actually much better. So that's a very important problem to show that. But anyhow, so these are the things. Any questions so far? Okay. So let's continue. So, you know, that's the thing that I like about Zoom, that you will just click and everything will be, this is much more, I mean, other one, if there is a chalk or other pen or something, you will feel it. But here, by a click, everything will be gone. Okay. Good. So, okay. So these are the areas that we discussed. So we consider this common technique, because these common techniques, they generally go through the reductions. So for this class, I think I assume that you have some general knowledge about algorithms, because these reductions actually, so in some sense, As I mentioned, this is algorithmic in a sense that we try to say that algorithm cannot do better, but ironically, we are using algorithms to show that you cannot do better than that. That is mainly through the reduction part. And actually, the earlier course, I think we may call this course actually like algorithmic lower bounds or fun with hardness. And that's the thing that we call it hardness for the name of the book. And then we had column assumptions and reductions, because that's exactly the thing that we are considering. As I mentioned, this can be considered the advanced algorithms course because we talk about the different areas of algorithms. And so like this one, let me. Good. So, yes. As I mentioned, so we consider. I mean, so in this course, what do you know? You will know. So you will know the limits of algorithm design in different fields. You will essentially you will master some of these techniques. Hopefully, the key problems, which are the assumptions, and the key reductions. These reductions, generally, as I mentioned, these are algorithms. You will see what are the proof style. Of course, I mean, this algorithm, we need to prove that they work. They are some kind of, sometimes these algorithms would be in the forms of gadget. Sometimes, I mean, the regular algorithm, sometimes would be gadget. Gadgets are still the algorithms way that, but it might be, I mean, somehow is like the different, I mean, some kind of gadget of algorithms, or gadgets you can consider different parts. If the reductions is like, if the overall algorithm is very complicated, we may have some smaller part, we call them gadget, and we talk about. And there are cool connections between problems, as I mentioned. That's also interesting, that you know that, oh, this problem and this problem seems very unrelated. This happened actually several times for us. It turns out this problem is in game theory, this problem is wireless communication. And it turns out actually all of them would be the same problem. They are the same problem, but they are not clear. And so we will understand this one. And also, I mean, there are some fun problems as well. So some of them, actually, we are talking about the different games. Actually, nowadays, for example, the most complicated design, the most complicated areas in MP completeness are the areas for proving games are hard. And I mean, we will talk about some of them in this one. These are the fun parts, and you can do some of your project based on that. But anyway, you can also look at the website of Eric Demain and myself, and of course in the book, and you can see more information from this. So if you search Eric Demain, algorithmic lower bounds, or fun with hardness, you will find that book as well. So as I mentioned, so the background is that you know some algorithms, asymptotics, combinatorics, and some complexity backgrounds. You need to pass the 451 or an equivalent course. This is like essentially senior algorithms. And so I think we talked already about let me just bring this one. Okay. So I already talked about the requirements, so I don't need to mention that. Just the topic, and I think we are done for today. So the topics that we are, I mean, we talk about MP completeness a lot. Some important problems like 3-SAT, 3-partition, Hamiltonicity, geometry, and 3-coloring. These are the problems that I mentioned for the, like, these are for your scribe notes part. That we are this way, we say that for MP completeness, these are the important problems that you can consider it, and you can find your, these are the assumptions in some sense that you can use it and give the references for them. These are the like 5 problems. Maybe you can add, I mean, for MP completeness, you can do a lot of more problems, but some other area would be less. That's the thing, that you will find the important problems and add it. Say, oh, these 5 problems are so important. This is the problem. You need to define the problem. This is the problem. This is the reference for that, for the later work. And this is the current result that exists for that. So for example, this problem is MP hard or something. We talk about the PS space and exponential time. We talk about inapproximability for approximation algorithm. We talk about fixed parameter tractability. we talk about, these two are called fine grain complexity. Fine grain. So what are these fine grain complexity? These are the one that we talk about. I mean, some problem like three-sum or all pair shortest path, and these are the one that, as I mentioned, these are the problem in P that we cannot say. For example, the running time for three-sum is n square. It is very important. Can we do it n to the 2 minus epsilon? Or all pair shortest path between graph, it is n to the 3. The question is, can we do it n to the 2.999? That's a very important problem. I think probably nowadays, these are all, if you do it, generally, you definitely will get a best paper award. So if you can get all pair shortest path, you can get n to the 2.99. When you submit the paper, you can, this is the example that I will mention. You can thank the referees. I mean, when you submit the paper, it says that in the abstract, you can say this is the result that we obtained. In advance, we thank the referees and thank the program committee for giving best paper award to us. So you can write that in the abstract. It might be funny, but actually you can do that because this is guaranteed that gets the best paper award, if it is correct. So these are the problems that we will talk about. This is within P. There are some other counting problems and uniqueness that we discussed. Some of them are also in the book. Algorithmic game theory, if we have time, we will talk about them. So what we talk about undecidability, if there is a time, we talk about streaming algorithms and map reduce algorithms. These are for big data algorithms that the lower bound exists, and online algorithm if we have time. And I think the references I mentioned before, it said that currently there is no textbook. I will just cross it out. There is a book, you can just read it from that I showed at hardness.mit.edu. And also, I mean, one other interesting thing, it would be good to, if you know 451, in general, you need to know about graphs, combinatorics, etc. Great, so I think we are done, and we will talk more. This is the overview of the course, and I defined actually some important things like about assumption and reduction. So later on, we will go there and you will just see the examples. Any questions, comments? Great. So if there is no questions or no comments, I think we are just finishing this session. And as I mentioned,